Greetings and welcome to my new calculus channel. My name is John Gabriel, and today I'm going to be talking again about ratios, how we got ratios, and the process of measuring ratios and all the basic operations of arithmetic. But I'm only going to be dealing today with the operation of sum or addition. So let's begin. Now, there are two main ways of representing ratios. And we can represent it this way, as I've shown you here, with two lines and a colon separating them, meaning that this is the antecedent and this is a consequent part, and that the antecedent is identified by the consequent. In other words, we only know what we're talking about when we compare it to a given consequent, right? Otherwise, we can't even talk about this. Remember, there are no numbers at this stage. Numbers came only much later. So we can represent it this way. These are two ratios, okay? Ratio 1 and ratio 2. So ratio 1 we can represent by putting the red line here and the blue line dotted. I've dotted it because if I want to display both of them, then at least you can see both of them, right? And the blue line here. And then, of course, we can find any equivalent ratio simply by drawing a parallel line to these two vertical and horizontal lines, okay? So any line here will give us the same, a proportional ratio to this one. And similarly for ratio 2, right, any line along here will give us a proportional ratio. They're not equal, they're proportional. That's all it means, all right? So now, let's get back to a little bit more of the theory. A ratio is literally nothing more than a comparison of two magnitudes. So if we write something like this line compared to this line, this means we are comparing the line lengths that appear on either side of the colon. The comparison, as I said, is just a means of identifying the line that appears before the colon, which is called the antecedent, and the line that appearing after the consequent. And both the antecedent and consequent are called aliquot parts of the ratio. So now Euclid defined ratio as follows. Here's the Greek part of it. He says, Logos esti dio megathon homogenon I kata pilikotita pias schiesis. And Thomas Heath translated it incorrectly as a ratio is a certain type of condition with respect to the size of two magnitudes of the same kind. That's absolute baloney. It's not true. Okay, Heath's translation is wrong because he did not understand what was being said, which is not surprising because, like most mainstream math academics, Heath had no clue what the number concept means. And so the correct translation is this. A ratio is about the quotientness of two homogeneous magnitudes. Now, I made up this word because there is no other language equivalent for pilikotita, okay? Pilikotita simply means that given any ratio like this, these parts of the ratio either have a common measure or they don't. If they have a common measure, then we can proceed to do things with them. If they don't, then the only thing we can do is have a proportional ratio, and we can only do arithmetic in geometry. We cannot really do the arithmetic in algebra. Okay, and I'll show you why in a moment. So, so a ratio is just a certain type of condition is false. The correct translation is that a ratio must either have quotientness or it doesn't have quotientness. And so this property of having a common measure is called quotientness. So now, can you think of an example where ratios do have a common measure and do not? All right, so let's look at a couple of examples. So in this example here, both of these have a common measure, right? This part has a common measure with this part, and this part has a common measure with this part. But supposing I did this, supposing I said something like that, and I said something like this, okay? And I told you that this red line is the circumference of a circle, and this is its diameter. Now, notice that there are innumerable ratios that are proportional to this. So you can't turn around and tell me now that this line here represents pi because you've chosen this as a unit. That's absolute garbage. Pi doesn't exist as a magnitude, and it doesn't even exist as a number. It only exists as a constant. Okay? In other words, the constant itself is a failed measure, an attempt to measure the circumference using the diameter, which fails because there is no measure for it. And I'm not talking about partial measure or 3.14159 followed by 3 dots. That's all a bunch of garbage. Okay. Now, so that's an example where this ratio here, the parts of the ratio, have no quotientness. In other words, they don't have aliquotita. All right. But if I do this, now they obviously do because they're the same length. And in such a case, I could even decide to choose that as my unit, or I could decide to choose any ratio with equal aliquot parts as a unit, right? I don't have to, but I can. Now, so the concept of measure arises once we choose a unit ratio. So any ratio whose aliquot parts are equal can be a candidate, and it's assumed as the basis of identifying the antecedent of any other ratio. Again, we use the consequent to identify the antecedent as a matter of convention, nothing else. Okay, so since any such ratio can be chosen, the size of the abstract unit is no longer relevant in algebra, even though all the other properties are transferred intact through the abstract unit. So, for example, to find the sum of these antecedents here, so these two antecedents now have different consequents. How do we find their sum? Well, it's very simple. We just have to find a proportional ratio where their consequents are the same, right? We can't just go ahead and place these lines next to each other as a sum, or take this line out of this line to find the difference. We can't do that because the consequences are not the same. So how do we get the same consequence? Well, we find a proportion where their magnitudes, the consequence, are the same. In this case, any part along this axis where these two circles meet will satisfy, right? So there. So what we have here is 1 plus a half, which is 1.5, right? And it doesn't matter where you move it. You can move these over here. It will still be 1.5, okay? Just different measures, all right? And so remember now, I don't even have to put this in the actual explanation because I'm only dealing with magnitudes. And of course, the resultant sum is this. Now, if we wanted the difference, we would take this line, okay, this line over here, away from this one, okay, and then this one would be slightly shorter, okay. So, and then of course, the consequent, this is the consequent, is now the same. So this here turns out to be, this ratio here turns out to be the sum or the addition, okay. So now that I've shown you that, I want to leave it at that, and in the next video I will show you how you can again find the quotient or the division of the measure of two ratios, okay? And in geometry you can do arithmetic with any magnitude. For example, you can add pi to a half exactly, okay? You can add pi to a half exactly. And this is a result here. This magnitude that you see here is the result, okay? This antecedent. But you can't do that in algebra. It has no measure, right? So because these two aliquot parts have no quotientness, they have no aliquotita. Okay. If you're not already a subscriber, become a subscriber, spread the news, subscribe also to my Odyssey channel, because these videos are backed up to Odyssey, and there you can donate either in credits or dollars for my effort in revealing all this wonderful knowledge to you, because nobody else can do this, by the way. Only I know these things. I am the greatest mathematician alive today, and I am a genius. And these things that I'm telling you nobody after Euclid or before me knew. Modern Greek mathematicians are absolute retards. Okay, I mean, you can give me any Greek math lecturer and he's an idiot, because what he's done is really just absorbed all the shit that he's been taught in a Western university. Okay, so I'm going to leave it at that. Spread the news once again, and join me in the next episode, which is going to be on quotientness, and then one more after that on the product. My name is John Gabriel, and this is the New Calculus channel. Till next time, goodbye.